Okay, welcome to the discussion on the topic analysis and design of beam in pure bending. So, this is also part of this unit 3 flexural stresses and beams, which is part of the syllabus in the course of strength of materials 1. So, in this particular section, what I am going to cover is um, to compute the maximum allowable stresses due to pure bending for a circular section. Okay, so I am hoping by the end of uh, this particular discussion that you are in a position to compute the maximum or allowable bending stress for the beam with circular cross section when it is subjected to pure bending, right? At the same time, you will also in be position to compute the cross sectional details for a beam when the details of the permissible bending stress is known to you, of the given material is known to you, as well as the span and loading positions are all provided, right, in that case, right? So I am going to now start before this particular discussion, wherein mainly the first part, it was taken here just to illustrate how the bending equation provides us the results that are required for analysis of particular members when only pure bending is concerned, as well as the second case. In the second case, we are dealing with how the design details are provided when the bending moment details or the moment maximum moment for a structural member is provided. We should be in a position to calculate the breadth and depth or cross sectional details of the beam, right? For this, both are worked out using the flexural theory. So the main equation that we are going to use is the pure bending equation, as we have used it and done earlier. So the main equation I am going to use throughout the discussion is m by I is equal to f by y, or you can say sigma by y. So this is the equation that I am going to use for explaining these two concepts, right? So let's see. So let's take a numerical example where we can illustrate these 2 points. So the first one, you have been given a case here. The cast iron pipe of external diameter was provided 40 mm and internal diameter was provided. That means it is a hollow cast iron pipe. Remember that. And then there was the length of the pipe was also provided as 4 meters, right? But at the same it is also supported at the ends. That means it is a simply supported case and carries a point load of 80 newtons at its center. So that is the situation. What you are expected to calculate is the maximum stress developed or induced in the cast iron pipe. So you can first of all represent the information given. So you have been given the data like this. There is a cast iron pipe. Okay. So this is the cast iron pipe that you are having. It is having a length of 2 meters, right? Sorry, 4 meters. It has a length of 4 meters, and uh, the interior and exterior diameters were also provided. Okay, this is the cross sectional details. So the interior one is 20 mm. Okay, let's know, somebody may be not able to see the right and other side of that. So this is a cross section. So this is 20, and the outer is 40. Okay, so these are the details. I hope I was not so accurate in drawing. So this is 20, this is 40. Okay. Okay, or you can, for the sake of your understanding, I can exaggerate, draw it. It's not a problem. Just to illustrate, this is the inner one, 20, and there is the external as 40 mm. So this was your hollow cast iron pipe cross sectional details. Okay, now you are expected to calculate the maximum stress. In essence, what you have been provided is the cross sectional details of the length, the outer and inner diameters, DO, outer diameter, inner diameters are provided. Okay, so actually it was written in a reverse, right? External is 40 and internal is not, no, this is 20 only. This is not 16, so it is a typographical error. So 20 mm, and there is a load of 80 Newton that was also given here. Okay, and target is sigma. So as I mentioned, this is your sigma max you are supposed to calculate the maximum stress. So sigma max formula from the bending equation m by I equal to f by y. You want or f by or sigma by y. Your equation will become m max. Right? Whenever sigma max is there, you must take m max. M max by I times y max. That's going to be our formula. Remember, this was again taken from the same bending equation, nothing else. I am showing here. Okay, max y max. All right. So that's what no, the equation is all about. Now, if you know these terms, your solution is ready. So, how to get that? So, first thing is there is a point load also there here, the center of the beam. There is 80 kilonewton, 80 Newton load is there. Because we require M is associated with both load and as well as span of the beam. So for a simply supported beam with point load, the maximum bending moment is WL by 4 and it will be in the shape of a triangle. This is the fundamental from the shear force bending moment concept. Okay. So you got, what was this moment? WL by 4. What is WL by 4? 80 times 40 W times L by 4 by 4, that becomes 80 Newton meter, because 4 get cancelled out from the both term. So you will be getting 80 Newton. So this was known to you. So your M max is nothing but 80 Newton meter. M is nothing but 80 Newton meter. Whenever we express moment, it should be written in mm. So therefore I am writing 80 Newton mm into 80 Newton mm, where it becomes 80 times 10 to the power 3 Newton mm. So you are ready with one quantity. Then I is for a hollow circular section. The moment of inertia is pi by 64 times capital D power 4 minus small d power 4, or you can say DO, outer diameter, okay, to the power 4 minus inner diameter, interior diameter or internal diameter, DI. Or somebody can take this as capital D and small d representing the outer and inner diameter. It doesn't make any major difference. Either way you can take. So here you can work out this. So you will be getting some value of I here, right? So DO here, now if you substitute that, because in here in mm, while doing calculation, it is always better to use no reasonable units, so that your calculation will be simple. For example, if I use here in centimeters, that will be simpler. So pi 4 to the power 4 minus 2 to the power 4, right, into pi by 64. So that becomes an easy calculation. Later on you can convert into mm power 4, because that's what we want in mm. So if you simplify, it is something like 256, 4 to the power 4, right, and 2 to the power 4 is 60. So 240, right? So 240 pi by 64. You can simplify that. So on, so cm to the power 4, cm power 4. So you got I also ready with you, right? Then y is nothing but the maximum diameter by 2. That is, y max is nothing but simply is total is 40 maximum, right? So y will be 40 by 2, because from the neutral axis your maximum will be, this is your y. So this becomes 40 by 2. So y max is also 40 by 2. So everything is known. You can simply substitute this to get the solution, that whatever you require. So 20 mm. So everything was ready. Thus, okay, simply substitute. So you can just go look at the solution. So I is that what we have calculated. Both are same. If somebody want, you can just check it. 240 times pi, right? We got 240 times pi by 64. How much you got? 11.78, right? Into 10 to the power 4 mm power 4, because this is in centimeter. So when you convert, so same value, 11.78 times 10 to the power 4, or mm. If you take in mm, either way you can write. Okay, you want to put a point here, it becomes 10 to the power 4. Okay, so I is there. and this is 80 as we told. I think in the problem it is not K, because it is given in Newton, right? So this is again another typographical error. And this is 40 by 2, which we have discussed. Simply substitute, you will get the stress value as this much. Okay. To bring the 20 this side, you are expected to calculate the sigma, so you can get that. That's all about the analysis of a pure bending situation in case of a circular cross section. Okay. Now let us look at one problem regarding the uh, what do you call computation of the cross sectional dimensions or design aspect in relation to pure bending. Suppose there is a structural member and the structural member is subjected to pure bending, and you have been provided the details of the maximum stress as well as load and span and expected to find the cross section, right? Look at that. This is the question that was taken in this regard. We have an Edwin beam, rectangular section, carries a load of 2 kN. So the load was given to you where it is acting at mid position. So the position and the magnitude and the position of the load was given, which is essential, right, for calculating your bending moment. The beam is simply supported over span. That means conditions of supports are simply supported. Load is 2 and placed centrally, it is a beam, simply supported beam. If the depth of the section of the beam is twice the breadth, okay, that means there is a condition given. Suppose B is your width and D is your depth, it was given as 2B is the width. It is not to exceed, that means he has given the permissible bending stress 9 Newton per mm square, and he is asking cross section, that means he is asking B and D to calculate. So if you represent the details of the beam, basically it is a rectangular beam. Okay. It is a rectangular beam. And the span of the beam is 3.6 meters. And the cross sectional dimensions are not known, but still we can, with the given hint, we can say that this is B. We assumed this is B, and based on the condition given, depth is twice the width. Okay, and there is a point load. The load acting is 2 kilonewton at the center. As we have discussed just now in the previous case, whenever load and its load position and the span were given, you can immediately, a type of load mentioned, then immediately calculate the moment. So what is again, it is a central point load. The moment is going to be a triangular shape moment diagram with a maximum value of WL by 4 at the center. So this value is 3.6 times. So sorry, not 2 times WL, right? W 2 times 3.654. So say 1.8. That is your value of the bending moment. That is the maximum bending. Yeah, before doing this, we have to set our plan, right? What we are supposed to find is BD. So how to get BD straight away? Is there any term in the bending equation representing B and D? Right? See, we are told that all our calculations will be using this equation only, m by I equal to sigma y or f by y. So sigma y, right? So sigma is provided to you, y is not known as a point, and bending moment we can find out, which we have found out as 1.8, and I depends upon BD. So which was a term which is no supposed to supposed to be worked out is I, because m is known, sigma is known, and y is no also y is supposed to be found, but we can express in terms of unknowns. So the unknowns are b and d, right? So because we want I, except I, everything you have to shift to the other side. So when I, if I bring this side, what I am getting, my by sigma, or m by sigma times m by sigma times y max. Okay. So, but this m value, sigma value are given, y I can write in terms of the available details. So here, moment of inertia, because the loading is in y direction, I becomes your ixx, that ixx becomes, because I already told, moment of inertia, it will be always, it should be calculated in a direction perpendicular to the direction of the load. Loading is my direction, therefore I am taking Ixx, and Ixx formulation is BD cube by 12, where B is for the what is the width. So that is not known to us. That is what we are supposed to find, and depth is 2b, because twice the depth width he told, right. So 2b cube by 12. So you can simplify this. Okay. So you will be getting somewhere as 2/3 of b power 4, because 4 twos and 4 threes. 2/3 of b to the power, that's all, b to the power 4. So you have everything now. Even b, what is y? Y is y max. So in the depth direction, you can put d by 2. D by 2 is nothing but b. So everything you substitute, you can straight away get your value in terms of your b value you can get, because everything you can convert. First of all, one can get either b or d. It's not a matter, because if you are substituting everything in terms of b, eliminating the other quantities, then you will be getting first b value. Or if you are eliminating all constant and keeping only d in the equation, you will be getting first b. So choice is ours. So now once you got that, so you simply substitute, the only unknown is b. So you can look at this. The moment we have worked out, the moment of inertia we have written as 2 by 3, and y is y max, which is nothing but b. Now you substitute. Okay. If you substitute that, you will be getting b as this much. Okay, 66 point something, and is this. Because it is difficult to provide this much accuracy, will be round off these values generally. Okay, so that is 65 and 130. Okay, this is about the analysis and design of the beam in the pure bed. Okay, so here in this case, the only point you have to observe is everything was worked out from the flexural bending equation, only, right? While doing so, one time we may be solving for analysis type of problems, or sometimes we may be solving design type of problem. This is one such example where we have used the design, we have calculated the cross sectional details, which is nothing but design part. Okay, so that's all about this. Thank you very much.